All right, we're still going to find the domain and range of these functions. Let's take a look. Now, we had talked about before about the fact that you can look at those that work, or you can look at those that don't work in terms of the x values when we're looking for domain. When we look at a rational equation here, where we have a fraction and we have an x in the bottom, what we want to focus on now are those that don't work. So we take everything in the bottom and we say that cannot equal 0. That is our domain. We can say, as far as writing our domain, domain is all the values of x such that x cannot equal 0. Now, for the range, that's going to be a little bit harder. What we can do is take a look at the graph of this. If we start plugging in points, if we put in 1, we get 1. If we put in 2, we get a half. And we put in 1/2, we get 2. This should be enough to kind of jar your memory. We looked at this the other day. This graph looks like there. Similarly, if we plug in -1, you get -1. -1/2, you get -2. And then -2, you get -1/2. So this graph looks there. Now, what's going on? So if we were actually going to write all this down, we could say, when we have a restriction on our domain, we want to see what happens to the graph as we get close to that restriction. So as x gets close to 0 on this right-hand side, what's the graph going to? It goes up to infinity. As x gets close to 0 from the left-hand side, what's the graph going to? It's going down to -infinity. What happens as x gets really big? This graph is going towards 0. Does it ever touch 0? No. Similarly, on the other side, as we go to -infinity, this is also going towards 0, but it never touches 0. And in this case, for our range, we'll have y cannot equal 0 as well. Another way to write this, we could say -infinity to 0 union with 0 to infinity. We want to be comfortable with both notations. Now let's take a look at this next problem. Similar to the first one, we said, okay, what's in the denominator? No matter what it is, it could be a quadratic or a cubic function. It doesn't matter. We're going to take that thing that's in the bottom and we say it cannot equal 0. So in this case, we just have x cannot equal 3. So our domain here, x such that x can equal 3. What about our range? Well, we know x can equal 3. What we're going to do is we'll have an asymptote there. We could quickly get some points again. If we plugged in 4, that would be 1. 3.5 would be 2. And then 5 would be 1/2. So what is this graph compared to the one we graphed in part A? It's almost the same graph, except it's going to be shifted over 3 units. So now when we take a look at this, what's our range? Well, again, we're going to be going up to positive infinity, down to -infinity. It's coming towards 0 on both sides, or from positive infinity, and as x goes to -infinity, but it never hits it. So our range in this case is going to be the same thing. All right, next one, absolute value. What's our absolute value graph look like? Well, before we can do that, is there any restriction? Can you take the absolute value of any number? Sure, there's no number, real number, that you can't plug in there. So what does that mean? That means it's all real numbers. I'll write that in just a second. We'll have domain such that x is a real number. Now, what about the range? What does the absolute value do to the input values, do to this, all the x values we plug in? It's going to make them positive or 0, because if you plug in 0, the absolute value of 0 is 0. So our range will be y is greater than or equal to 0. If we take a look at our graph, if we say 0, plug in 1, we get 1, 2, 2, negative 1, we get negative, or positive 1, and negative 2, we get positive 2. This is 2 rays that form a V. And our range y such that y is greater than or equal to 0. Let's take a look at this next one. What is this doing to the graph? Now, you can kind of think of this as, what if this said, how would you treat it if it said x plus 4 squared plus 1? Well, this would be a parabola, and the vertex would be moved 4 units to the left and then up 1 unit. Well, that's exactly what's going to happen to there. We'll talk more about that. And you can think of this as, if I plug in negative 4, I'm going to get 1. So negative 4, I get 1. If I plug in negative 3, I'll have 2. Negative 2, I get 3. And 5, negative 5, I get absolute value of negative 5 plus 4. Absolute value of negative 1 is 1. Plus 1 is 2. And at this point, hopefully you can see that. If we do negative 6, we'll get positive 3. And this graph is looking the same way, but it's shifted over. Now, let me just put here that we're comparing it to this one. So what's my domain here? Well, again, my domain is going to be all real numbers. There's nothing I can't take the absolute value of. But now my range is going to be different. When I'm looking at this, I can look at my graph. If I kind of think of that shining a light on it, I could do that as well, or I can look and see what's the smallest y value I have here. My smallest y value is 1, and I can have everything else greater than that. So my range would be y such that y is greater than or equal to 1. All right, a piecewise function. This is called a piecewise function because it's defined in pieces. We are given 3 different pieces for this graph, and we're given a specific domain to graph each one. So this is basically saying graph y equals x minus 1, that's this first piece, when x is in between 0, negative 2, and 0. Well, let's go ahead and do that. We know this is a line. If we plug in negative 2, we'll get negative 3. So negative 2 will go down to negative 3. Now it's not equal to there. It's only strictly, x is strictly greater than that, so we'll put an open circle there. And it goes all the way up to 0, and we know that y-intercept is negative 1. And so we'll have an open circle there, and we'll have to take a look and see what happens in the next piece to see if that changes. So now, this is a line, y equals x minus 1. Here's that piece, but it's been restricted on the domain, so instead of a line, it's just a line segment. At negative 2, it's not equal to, so it's open circle, and the same thing at 0. And that's the only part of y equals x minus 1 that we can graph. Now I could kind of set up my table here to show these values that I was just mentioning. Now let's take a look at y equals x squared minus 2x minus 3. That's that second piece. But do I just graph that everywhere? No. I'm only going to be graphing it between 0 and 3. Now technically this should, I just realized that I should have labeled this u, and this should be g of u. Because we're not talking about x and y. I'm just using x and y so you can become more familiar with what's going on here. All right, we know this is a parabola. It's a quadratic equation. It opens up. When we plug in, we can plug in, we only have 0 in terms of integers, 0, 1, 2, 3. Let's see what happens. 0, 1, 2, 3. Plug in 0, we get negative 3. Plug in 1, we get negative 4. 2, we get negative 3. And 3, we get 0. So at 0, it's negative 3. Now it's equal to at x equals 0, so I'm going to have a closed circle. And then I'll have plot all the points, 1, negative 4, 2, negative 3, and again a closed circle at x equals 3. And I'm going to connect the dots. And I have closed circle because it's including both x equals 0 and x equals 3. And then for the last part, we'll have y equals 0 when x is greater than 3. Well, y equals 0, that's a horizontal line. Now technically we have an open circle there, but it's right on top of this closed circle, so we won't see the open circle. And y equals 0, it'll just be a horizontal line here. And since it's all values of x greater than 3, where it's on the x-axis there, and we just put the arrow there nice and thick so we can see it. And that's basically it for a piecewise function. So how do you go about graphing a piecewise function? You look at each piece and you graph it for its domain, for that specific set of x values. And then you look at the next piece and graph it for those specific x values, etc. And you need to take into account whether or not it's greater than or equal to, or is it less than. If it's less than or greater than, then it's going to be an open circle. And if it's greater than or equal to or less than or equal to, it's a closed circle. If you have an open circle on top of a closed circle, the only thing you're going to see is a closed circle.